So this is a problem from a relatively older midterm from 2012, first midterm, problem 2. And here you have two spherical shells. So we have a cavity outside this, a non-conducting spherical shell, and outside this we have a conducting spherical shell. And the radii are A and B and C. And you can find a much more clear picture in the document on ODTUClass. They're saying this, okay, this has uniform charge density rho. The inside spherical shell is uniform charge density rho, and the outside is initially has no net charge. Express your answer in terms of sum of the all given quantities. Using Gauss's law, find the electric field as a function of radius r for distance a less than r less than b. So they're asking A of r for a less than r less than b. So inside this inner conducting shell. Now, and they're explicitly saying using Gauss's law, so we don't have, we cannot do any tricks, we cannot apply Newton's theorem from gravity and so on and so forth. We have to be honest here. So what we do is we draw a hypothetical Gaussian surface of radius r to find this. And we just write down Gauss's law in this case. So E dot dA is Q enclosed by epsilon naught. Now, the electric field here by symmetry is going to be in the radial direction. So the electric field is going to look like perhaps this over here. And because this is a sphere, the sphere we chose is concentric with our spherical shell, the surface element is also going to be in the radial direction. Remember, it has to be normal to the surface. And so these are parallel to each other. We can turn this dot product into a regular product. Okay? So this becomes EDA. Furthermore, we have spherical symmetry, which means that anywhere we go on the surface of the sphere, things are going to remain the same. In particular, the magnitude of the electric field has to remain the same, so we can take it out of the integral. Okay? So this becomes EA. And now this surface integral over the surface elements just becomes the surface area of the sphere, and that is given by 4 pi r square. Okay. Now comes the question of enclosed charge. So this enclosed charge is going to be the charge density times the volume of this part that actually contains the charge. Not the whole volume, but just the part that contains the charge. So I'm going to say that this is rho times volume epsilon naught, with the understanding that this volume has to be only the part that contains the charge. And what is that volume? Well, that volume is the total volume of the sphere minus the volume of this cavity inside. So that volume is going to be 4/3 pi r cube minus 4/3 pi a cube. Okay. And now we can get some cancellations. 4 pi's are going to cancel. I don't know if you get anything much more than that. So E is going to be 1 over r epsilon naught r square. And in numerator it's going to be, there's a 3 here, r cubed divided by a cube. And it doesn't look very nice, but this is what we get, unless I made a mistake in the algebra. So for part B, find the surface charge densities sigma in and sigma out of the inner and outer surfaces, respectively of the conducting shell. So they're asking for the surface charge density over here at radius r, over here at radius b, and also at radius c. Now, how would you do this by using Gauss's law? One thing is to draw a hypothetical Gaussian surface over here. Now everything here does apply. You're going to get this over here, and on the right hand side you're going to get the charge enclosed. Okay? Now I'm talking about the surface charge density on this part. Okay? So if I'm drawing my Gaussian surface through the conductor this way, the electric field has to be 0. Inside the conductor, there is no electric field. So the left-hand side of this is 0. Now what about the right-hand side? The right-hand side contains the enclosed charge. Well, this is going to be my Gaussian surface, and it includes the charge in the insulator. It also includes the charge that's induced on the inner surface of the conductor. And because their sum has to come to 0, this means that the induced charge on the inner surface of the conductor must be equal and opposite to the total charge in the insulator part. Okay? So let's erase this. We don't actually need any algebra for this part. So for part B, sigma inner is going to be Q induced over 4 pi b squared, and that Q induced must be equal to the Q in the insulator over 4 pi b squared. And what is the Q on the insulator? Well, it is the surface charge density times the volume, and that volume is just the total volume of radius B minus the volume of radius A. Okay? So the Q insulator is going to be rho times 4/3 pi B cube minus 4/3 pi A cube over 4 pi B square. And again, there are cancellations. 4 pi's are going to go away. You can take into common parentheses of 1/3 and so on and so forth. But this is going to be the charge induced on the inner part. Now, what about the outer part? Well, this Q induced must come from the inside the conductor. That's going to leave an equal and opposite charge on the conductor, and that is going to move to the outer surface. Okay? So sigma outer is going to be minus Q induced divided by 4 pi c squared. Now this charge is going to get distributed on the outer surface, which is surface area of 4 pi c squared. Okay, and you proceed in exactly the same way. This Q induced is rho times blah, 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 blah. It's going to have a negative sign though, right? So the charges are equal on the two surfaces of the conducting part, but the charge densities are not equal because the surface areas are not equal. So charge per unit area is different, not because the charges are different, but because the areas are different. For part C, suppose that the point charge Q0 is placed at the center of a spherical shell. Find the electric flux through the outer surface of the conducting shell. Now, this is actually one reason why I wanted to look at this problem. Now, the physics is not that difficult. Okay? So what's happening here is that they're introducing an additional charge, Q0, at the center. This, of course, changes all of the Q induced, right? So Q induced, Q enclosed. So Q enclosed was rho times V. Now it's going to be plus whatever is residing at the center. For all of these Gaussian surfaces, you're going to have to add the Q0. Okay, but then they're asking for the electric flux through the outer surface of the conducting shell. Now, in my opinion, this is not a well-posed problem. So they should have said something like just outside the conducting shell, so through a sphere that's concentric and lies just outside the conducting shell, something like this, or just inside. Okay, now on the surface doesn't make sense. That's just, it's not physical, because there is some charge, Q out, sigma out, that as we just calculated, residing on that surface. So this surface is just passing through these charges. This is not something physical, okay? And there's a mathematical ambiguity. So if this is actually inside, then it's 0, okay? If this is outside, then that is going to be, so the electric flux is going to be, they're asking for the electric flux, is going to be Q enclosed divided by epsilon naught. And Q enclosed, as we have just seen, is just going to be rho 4/3 pi, B cube minus 4/3 pi A cube plus a Q0 divided by epsilon naught. Okay, so if it's just outside, this is the answer. If it's just inside, the answer is 0. I think it's ambiguous when it's on top, because that doesn't correspond to any physical situation. If there is no way to calculate electric flux if the surface you're choosing is passing through the charge, right? There is no such thing as a point charge and a surface passing through it. What kind of electric flux does this produce? It doesn't produce anything. Yeah, so that's perhaps what they're asking for, that this doesn't produce anything. Then you need to only consider the charge that's to the inside. Okay, so this is Q naught. There's some charge over here, and that induces some negative charge over there. So that's again going to be 0. Right? So the question is not well posed. It's a bit ambiguous, and I wouldn't really know how to answer this. But this is important, that if you think there's some ambiguity, you should still proceed. You shouldn't just stop. Okay? In a midterm, if you see a problem that you think is problematic, that it's not really solved with the information given, you should still proceed by making some assumptions, and you lay out your assumptions just accurately. So in this case, our assumption the surface lays just outside the conducting shell. Unless you make an assumption like this, I don't think the problem is solvable. It's ambiguous. But as I said, when you see a problematic question in the midterm, in the exam, you should not stop. You should make an assumption, something reasonable. Okay? So, for example, the other assumption would not be reasonable, saying that it's just inside and hence the flux is 0. That's a trivial answer. Obviously, that's not what they're asking for. You have to use some common sense. And having something problematic in a question doesn't give you a free pass. Okay, there's a problem, so I should get the full point whatever I write. No, that's not the case. Okay, as engineers, you are going to use some incomplete information. So this is one of those cases. It's not a good one. It's never pleasant to be given incomplete information, but you have to do the best you can. And the best you can is not to assume it's inside the outer surface and say the electric flux is 0. Okay, that's just an easy way out. It's not going to be accepted.